Hello, my name is Pranav Varun, and this is my final presentation for the Cybersecurity Industry Project, a security analysis of Modbus and MQTT, two popular, widely used protocols in water treatment industrial control systems. The, the company that's part of this project is Gradient. It is a water company that provides water treatment solutions to clients ranging from Coca-Cola to automobile companies and the Singapore government. Their headquarters is in Singapore and Boston. They have offices in Perth, Adelaide, and Sydney, mainly dealing with mining companies in Australia. And in the figure shown, it reflects a typical scenario where an operator sits behind an engineering station and a human machine interface to be able to remotely control a PLC, programmable logic controller, which is a computer that's programmed to control the sensors and actuators in the machines in the plants that are located rurally. The term Industry 4.0 is used today to refer to the fourth industrial revolution, heavily characterized by artificial intelligence, big data, Internet of Things, and cloud computing. And all this increased connectivity necessitates the requirement for increased security. Modbus and MQTT are used in these distributed control system environments. They facilitate interoperability between operational technology and information technology. In information technology, the biggest asset is data, but in operational technology, the biggest asset is the plant itself. The fear is losing control of the plant, something exploding, or the plant itself shutting down. So it's crucial to analyze potential attacks against these protocols and learning how to mitigate them. The objectives of this project are to design and deploy a cybersecurity lab that mimics a real industrial control system environment, analyze common attacks against the Modbus and MQTT, and then provide mitigation and prevention strategies. In part A, I set up a 3D simulation of a water treatment plant using the Factory IO software running on a Windows machine. And I use OpenPLC to create a virtual PLC that's been programmed using ladder logic to work with the Factory IO simulation, and I configured it to use Modbus over TCP/IP. And Modbus is a serial protocol that uses a master-slave model, and it was initially introduced in the late 1970s. Then in part B, I extend the Modbus data to now use MQTT, which is a protocol that was first introduced in the late 1990s, and it uses a publish subscribe model. And I use a Mosquitto broker, an MQTT broker running on my local machine, and I write a program and create a flow using Node-RED to convert that Modbus serial data into MQTT messages. The result of this project, apart from the creation of the cybersecurity lab environment, apart from the test environment, is the attacks that I've ran against it. which include recon and fingerprinting, packet injection, analysis of the communication, dissecting, analysis, uh, uh, dissecting the communication, running DOS, and dictionary attack. So apart from the creation of the test environment, the actual results of the project are the attacks that I have run against it, which include recon and fingerprinting, packet injection, an analysis that dissects the communication, denial of service, and dictionary attack. And in conclusion, Modbus and MQTT are inherently vulnerable because they don't have encryption or authentication built in. So, in a water treatment ICS, it's essential to try to use TLS to encrypt the communication, have access control lists to allow only authorized personnel to access specific features, and use scanning software like Nessus or OpenVAS to uh, uh, periodically look out for vulnerabilities and patch them. Then another strong recommendation would be to use a VPN to segment the network and make sure it's not available to the internet. And finally, using a SIM like Elk or Elastic or Splunk, and also using an IDS like Snot would be an excellent thing to look out for any intrusions or alerts or anomalous behavior rather. This is one of my favorite quotes that got me into this field, and thank you. Now I will go ahead and demonstrate the project to you. I'd like to now showcase the test environment and the attacks. Full details will be in the report though. This is a Windows 10 machine, and I have factory IO open here now, and this is a scene that I've created. It's got a water tank with a discharge and a fill valve, and there's a station showing the pH and chlorine levels. So if I press start now, it's not actually going to work because it's not connected to the PLC computer to run the program and make it work. I'm going to do that in a second, but I just wanted to show that this driver has an IP. It's got the holding registers here, and it's configured for Modbus TCP/IP. I have the virtual machine Raspberry Pi that has OpenPLC installed in it, and I've cd'd into the directory, and I'm gonna go ahead and start the OpenPLC, and I'm now going to go to this OpenPLC IP address and log in. And this is a dashboard for the PLC. I have the water treatment program listed here, and as I said before, it's a master slave model, and the slave device of factory IO has been configured with its IP and its holding registers as well. So I'm just gonna go back now and start the PLC. And now going back into factory IO, if I press start now, it should work. So as you can see, it's gonna start filling this tank with water. The pH level is now at 7, and once it's filled to the brim, it's going to decrease the pH level and increase the chlorine level, thereby disinfecting the water. And this is a very typical thing done in water treatment. I've also got Kali Linux running, and I've started Metasploit already, and I've set the IP address to the factory IO, and I've set the data address for 0, so it should be pH level, and I've set the number for 5, so it's gonna read 5 holding registers. The action is to read the holding registers, and going ahead and hitting exploit, you can now see that the holding registers are able to be read. I'm gonna now set the action to write register, and set the data to 80, set data address to 0, and run exploit. And if you see, it doesn't hold the value, but it does successfully write to that register, and this can be fatal to the actual process. Now if I start Node-RED, I already have the MQTT broker running on this machine. So this is my Node-RED flow that I've created to read the chlorine levels from the factory IO Modbus. It's connected to my OpenPLC. I've configured it here, and the chlorine levels are connected to the my local mosquito broker on my local machine, and all I have to do now is deploy. It's been successfully deployed. So if I come here to mosquito sub and subscribe to the same topic on Node-RED, that's over here, factory chlorine level. I've also used a username and password for this, and now I'm able to see the Modbus holding register converted to MQTT messages. Going back to Kali Linux, previously I used the Modbus client auxiliary scanner for the Modbus exploitation. I've got Metasploit running again, but this time using the MQTT Connect scanner. So someone with nefarious intentions could run a dictionary attack, and this is how they would do it. setting rhost to my MQTT Pro code. I've already compiled a password and username file and just hit run, and I'm able to get the successfully verify the username and password from my precompiled files, using which now I can subscribe to all topics and whatever has been running to my MQTT broker. I'm able to subscribe to those messages as well with the username and password that I cracked. And I've also created a Python script that can execute a DOS attack. So as you can see now, my flooding messages are DOSing the network, and that's my demonstration. Thank you.